So Unit 5 will be sort of our intro to trig units. We probably will not dive deep into trig until Unit 6. But Unit 5 is all about getting the fundamental ideas down, the basic shapes, basic ideas of these trig functions. And specifically, this section 5.1 is all about the things we should have gotten from geometry that will be really, really important for us when we talk about trigonometry. So as you guys can see, we have 3 lesson goals for this section. By the end of this section, we should be able to freely and comfortably convert to and from degrees and radians, find and identify coterminal angles, and lastly, find reference angles, which is probably one of the more important things to be able to do if you're going to be successful in trig. So unfortunately, this section will just be mostly understanding vocabulary, terminology, and ideas. We won't be actually doing anything with them. If this was an English class, to use an analogy, today we're going to be learning the alphabet, the individual letters. We're not going to be writing down words or sentences just yet. So let's start at the most basic ideas. Angles. All right. At the heart of trigonometry is the idea of angles. We're going to be studying angles and the relationships of sides to said angles. So let's just start at the very, very beginning. Let's define it. By definition, an angle is a measure of rotation between 2 line segments or rays. With one segment or ray called the initial side and the other called the terminal side. So every angle consists of 2 line segments or rays, the initial and the terminal. And the order in which you call the initial and terminals, they sort of matter. They dictate the size of the angle. So for example, I'm freehand drawing this, so it's not going to be super duper accurate, but I'm going to try to draw 2 identical pictures here. All right. Now, in the left picture, if I call this the initial side, and then this the terminal side, then the angle in question measures that amount of rotation. But if I call this the initial side, and this the terminal side, this is the angle in question. So the angle measurement always starts from the initial and ends at the terminal. Now you can see here I sort of drew these 2 random angles just floating in air though. And that's sort of a problem in math, because when one mathematician talks about angles to another mathematician, we sort of want to be on the same page. We sort of want to be talking about the same thing. So we have this idea that angles are said to be in standard position if the initial side is on the x-axis. So mathematician on the positive x-axis, to be specific. So mathematicians, we decided, you know what? Hey guys, every angle you draw, let's start on the positive x-axis so that we basically can be talking about the same angle, same size. So there's no ambiguity. We all, if you say 30 degrees, if you say 48 degrees, we all understand what everyone's talking about. So angles in standard position will always start on the positive x-axis. So the initial side will always start here, and the terminal side could be, I just drew something random. So the terminal side can be somewhere over there. Now the idea of an angle is purely convention. That is to say, it is an agreement within the mathematical community. It's not something that's found in nature, but it's something that we all agree, hey guys, let's do the same thing. So by convention, this means by agreement, angles measured counterclockwise from the initial side is said to be positive. So angles, even though it's an amount of rotation and physically it doesn't seem to make sense to have a negative rotation, but by standard convention we consider angles positive if you're measuring counterclockwise, and likewise negative if you're measuring it clockwise. Angles measured clockwise from the initial side is said to be negative. So I guess that the two random pictures that I drew before, if you had something like this, I would consider this positive angles. And if I had something like, I don't know, something below the x-axis, say here, went this way, see how he's clockwise, I would consider this negative. Now, I've sort of been very vague when it comes to angles, but when we talk about angles, we need numerical measurements. So there are lots and lots of different ways to measure angles. So you guys already know some units. Degrees is a very common way to use, but we have something called grads, and there are lots of different units. The two more popular units are degrees and radians. I hope I don't have to explain what a degree is. I hope everyone understands what a degree is. A degree is simply 1/360th of a circle. Now, ask me where do they get the number 360? I will be glad to share with you some theories, but I'm willing to bet money that not many, if any, of you guys care about where the number 360 came from. But if you are, please definitely ask me in class. But that's one way to measure angles. So ways to measure angles. We have two major systems: the degree system and the radian system. So degree by definition is 1/360th of a circle. Therefore, we have some implications. There's 360 degrees in a full circle. There's 180 degrees in half a circle. There's 90 degrees in a quarter of a circle. So on and so on and so forth, right? Let's see if it has an O shape. Close enough. So that's the definition of a degree. It's something that mathematicians just randomly made up. We decided, hey everyone, we're going to make this whole guy here called 360 degrees. Well, just by using proportions and common sense, that must mean half of a circle is 180, which means a quarter of a circle is 90, so on and so forth. But where does this idea of a radian come from? Well, radians are less arbitrary. They're not made up. Radian measurements actually comes from physical attributes of a circle. It is defined as 1 radian is equal to the angle measurement that subtends an arc length of 1 radius. Now, if you need a translation of that, this is what a radian means. Suppose you had a circle. I think that's a circle. We all know that every single circle has a center and has a set radius. Right. Actually, let me try to color code this. Well, if you were to take this radius and instead wrap it along the outer edge of the circle, so this length here, if instead we wrapped it around the outer edge of the circle, the same length, right? So this is 1 radius. Well, how much or how many angles is covered by that amount? We call that a radian. Right? So if you take a radius and wrap it around the circumference, the amount of angles that that radius covers is what we call a radian. So that's how we get multiple radians. Well, what does 2 radians mean or look like? It's as if you were to take 2 radii and put it along the outer edge of a circle. So this whole guy in this picture right there would be 2 radians, and then 3 radians would be 3 radii, 4 radians would be 4 radii, so on and so on and so forth. So that's all a radian is. It's just the amount that a radius wraps or covers around a circle. Now naturally we ask yourself, how many radians are there in a full circle? Well, a better question is, how many radii can fit on a circle? Right? Because the amount of radii that can fit on the circle should be the amount of radians. That's the definition of radians. Well, the answer comes from geometry. Recall that we have a circumference formula. Circumference of a circle is 2 pi r. This literally says a whole circumference is 2 pi radii, right? This formula for circumference, 2 pi r, it's a basic geometry formula we've all memorized. It literally says there are 2 pi radii in a full circle. You can fit 2 pi radii, or plural for radius, along the circumference. Therefore, a full circle is 2 pi radians. Hence, a full circle is 2 pi radians, and then you can do your proportions there. Half a circle is pi radians. A quarter of a circle is pi halves radians, so on and so on and so forth. So that's all. Radian is just another way of measuring angles. They do it in terms of radii, which uses pies, but that's totally fine. It isn't anything new or fancy. It's not something that, we can say degrees are better or radians are better. It's not competing with degrees. It's just another way of representing the same thing, angle measurement. It's just like saying, it's just like using feet instead of meters, or vice versa, yards instead of centimeters. So it's just a different way of measuring. However, mathematicians, they like radians because aside from the fact that it's not something that's made up like degrees, it's actually a physical attribute of the circle. Radians are considered a pure number, a dimensionless number, which does make mathematical formulas easy. Now, I don't care your philosophy beyond radians. I don't care if you don't care why radians are important. The thing that we need to be comfortable with is going back and forth between the two. So how do we do that? We need to know the conversion factors between radians and degrees. Here's the idea. Since 360 degrees is the same thing as 2 pi radians, right? The following are equivalent to 1. Well, if I take 360 degrees and divide it by 2 pi radians, notice how I don't actually write anything for radians. Typically, when it comes to angle measurements, if you use anything involving pi's, or heck, if you are talking about angles and you don't put any unit symbols, everyone understands you're talking about radians. Okay. Or if I take 2 pi and divide by 360, I know that these guys should equal 1. Now, these are not actually the conversion factors I use. I actually use the reduced versions. So if I were to divide by 2, I actually get 180 over pi, or pi over 180 degrees. So these are the conversion factors that I actually use. So to convert to and from radians in degrees, you just have to multiply by the appropriate conversion factor. Hint, you want to use a conversion factor that has the unit you're trying to get rid of in the denominator, because that's how we cancel out. For example, suppose I ask you to convert into radians, and I gave you 60 degrees. Right. Well, do you guys agree that to answer this question, I need to get rid of degrees? So which conversion factor will I use? Well, I will use the conversion factor that has the thing I'm trying to get rid of in the denominator. If I'm trying to change degrees, if I'm trying to get rid of degrees, I'm going to use the conversion factor that has degrees on the bottom. So you simply have to multiply this guy by pi over 180. And then you reduce. I can divide out a 60, so that's a 1 and a 3, and then you multiply straight across. So I know that pi thirds radians is the same thing as 60 degrees. That's basically it. It doesn't get any more complicated than that. You just multiply by the appropriate conversion factor. If I wanted to convert 75 degrees, you do the same thing. I'm trying to get rid of the degrees, so you put the degrees on the bottom, and then you reduce as much as possible. What can we divide out? I know we can divide out a 5. So what is that? That's a 1, 2, 5, and this will be a 3, 36. Can I divide out any more? Yeah, I can divide out a 3. So this will be a 5 and a 12. That's it. So we have 5 pi over 12. Doesn't matter if the degree is positive or negative, it works the same way. So let's say I wanted to convert negative 120. Again, I'm going to multiply by the conversion factor. I want to get rid of degrees, so you multiply by the 180 that's on the bottom. And then you can reduce. I think I can reduce out, let's see, I can cross out a 0 and then divide out a 6. So that becomes a 2 and a 3. So we have negative 2 pi thirds. Right? Converting the other way, easy peasy. Suppose I wanted to convert into degrees, and I wanted to convert, say, to pi thirds. Okay. In this example, I hope we agree that we're trying to get rid of the radians, so I'll use a conversion factor that has the radians on the bottom, meaning the 180 degrees is on top. And then you just cancel and simplify. I can cancel the pi's, and I can reduce by 3, and that gives me a 60. So 2 pi thirds is the same thing as 2 times 60, which is 120 degrees. Again, it doesn't matter if your radians is positive or negative, converting is the same. So suppose I ask you to convert negative pi fourths Okay, that's easy. Multiply by the conversion factor. I'm trying to get rid of radians, so I'll put the pi on the bottom. And then you just reduce. The pi's will cancel, and I can divide out by 4. And that's going to give me a 45, and that's it. The answer is negative 45 degrees. In geometry, there are these things called quadrants. And quadrants are sort of just like locations. They sort of describe where angles are. So in a normal Cartesian plane, we always start in the top right corner, and we'll label that as quadrant 1. And then we go counterclockwise, because in angles, for whatever reason, we measure counterclockwise. So the top left corner is quadrant 2, bottom left corner is quadrant 3, and bottom right corner is quadrant 4. And one of the things that we need to be proficient at is understanding what quadrant an angle is in. Knowing that these quadrants, the prefix quad, separates everything to fourths. So in a degree system, we should know that this is 0 degrees. Let me use a different color here. 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Or in the radian system, 0 radians, pi halves radians, pi radians, 3 pi halves radians. So we need to be able to classify an angle based on its quadrants. So for example, state what quadrant the angles are in. Letter A, 70 degrees. Well, since I can see that 70 is between 0 and 90, it's in quadrant 1. Letter B, say negative 190 degrees. Now you got to remember that negative angles, instead of going counterclockwise, you actually have to count clockwise. How do you do this? Because our labeling is for positive angles. You just have to remember that every quarter is 90 degrees. So here's negative 90 right here. Then we'll go to negative 180. So negative 190 should be a little bit more. Hey, it's in quadrant 2. Right. And we need to be proficient in both radians and degrees. So what if I ask you 5 pi thirds? Now, if you're not good at radian measurements, notice how more likely than not, the radian measurements are in terms of pi. So if I want to know where 5 pi thirds is, just ignore the pi and look at the numbers part. 5 thirds. Well, what is 5 thirds? 5 thirds is approximately 1.666, so on and so on and so forth. Well, if you look at the numbers part without the pi's, this right here is half of a pi. If you ignore the pi, it's just 1/2, 0.5. This is 1 full pi, 1. This is 3 halves pi's, or 1.5, 1.5. So I hope we can see that 1.666 is a little bit more than 1.5. So this guy here has to be in quadrant 4. So that's the thought process. If you have difficulty in envisioning radians, that's the thought process we need to have. Do note angles that lie exactly on the x or y axis are called quadrantal angles and do not have a quadrant. So it wouldn't make sense to say, what quadrant is 90 degrees in? Because 90 degrees is the positive y-axis. The best thing you can say is it's between two quadrants. So I wouldn't say 90 degrees is in a particular quadrant. I would say 90 degrees is between quadrant 1 and quadrant 2. Now, angles are not limited to a full circle. If you have angles that go beyond a full circle, positive or negative, we call those coterminal angles. So the definition of coterminal angles are angles that go beyond a full circle positively or negatively. Actually, that's not the official textbook definition. That's sort of my layman's terms definition. What does the textbook say? The textbook says coterminal angles are angles that share a common terminal side. Right. But the only way you can do this, of course, is if you go beyond a full circle. So, for example, right, if I had an angle, let me draw a quick coordinate system here. If I had, say, this angle here, and I went this way, so there's one angle. But instead, what if I went a full circle? So I went something like, here's a full circle, but then I kept going and landed on that same spot, so I'll call this theta prime. Both of those angles, the black angle and the blue angle, because there's technically a little line here, a terminal side here, both the black angle and the blue angle are considered coterminal, right? And you can go forwards and backwards. It doesn't have to be big angles. You could have positives and negatives angles being coterminal with each other, right? So if I had something like, heck, in the first quadrant here, here's one angle, but what if I went the other way around? Here's the other angle. Technically, both of those are coterminal as well. Now, the idea of finding coterminal angles are super duper easy. All right, let's have ideas. Just straight up idea. Coterminal angles are always separated by multiples of full circles. Now remember the two systems that we're in, 360 degrees for a full circle or 2 pi radians. So what does that mean? Well, that means if I want to find coterminal angles, all you have to do is just keep adding or subtracting 360 degrees or 2 pi radians. For example, suppose I ask you to find one positive and one negative angle that are coterminal with 112 degrees. Well, that's easy. Since I want coterminal angles, all I have to do is add or subtract a full circle. Since we're in the degree system, that's going to be 360. Now, since they want one positive and one negative, that would probably tell me that I need to add and subtract. So let's find the positive coterminal angle. So to do that, you simply add 360, and we get 472 degrees. If you were to graph this guy and this guy, it's guaranteed that they'll land in the same spot. If I wanted to find a negative coterminal angle, just do the exact opposite. Subtract a full circle, 360. That's going to give us negative 248 degrees. Again, the idea is if you graphed him and if you graphed him, they'll land in the same spot. We need to be proficient adding, subtracting full circles in degrees, which is regular numbers, and radians, which is doing fractions. To check whether or not they're coterminal, all you got to do is repeated addition or repeated subtraction. For example, are the following pairs of angles coterminal with each other? And let's say I gave you 200 degrees and 2000 degrees. Well, to check this, I would have to ask myself, is 200 and 2000 separated by multiples of 360? The easiest way you can do this is start at one angle and constantly add or subtract to get to the other angle. So I could start at 200 and add full circles, 360 degrees, and see if I land on 2000. Or I can start at 2000 and subtract full circles, 360 degrees, and ask myself, do I land on 200? There is no right, wrong, easy, hard way to do things. Let's just subtract for the heck of it. So, okay, are they? Let's check. Let's subtract a full circle. That's going to give me 1640 degrees. Do you see how 1640 is still a pretty big angle? Let's subtract again. And that's basically it. You just want to keep subtracting until you check all the way down. So that's 1280, not enough. That's 920, not enough. That is 560, not enough. 200 degrees. Hey, exactly. What does all of this work tell us? All this work tells us if I start at one angle and I add or subtract by full circles, I am guaranteed to land at the second angle. That means these two angles are coterminal. So the answer here is yes, they are coterminal. Doing this with degrees and radians is the same idea. Again, all you have to do is add or subtract full circles. So let's do the same question. Is negative 19 pi thirds and pi thirds coterminal with each other? Well, all you have to do is add full circles. Now, in the radian system, a full circle is 2 pi. Now, I actually like radians. I actually like radians because they use fractions. I know that sounds weird. Fractions usually make things harder. But they actually make things a lot easier because you're always working with the common denominator. So if I want to add or subtract 2 pi, right? Notice what denominator we're using. Denominator of 3. So I have to ask myself, the number 2 is the same thing as how many thirds? And this should not be a hard question. Take 2 candy bars, chop them each into 3 pieces. You have 6 pieces altogether. So all you have to do is just constantly add or subtract 6 pi thirds. Again, it doesn't really matter. We can start here and add our way up, or we can start here and subtract our way down. It really doesn't matter. I'll go ahead and start at the negative. I don't know. I like to keep things positive. So what's negative 19 pi thirds plus 6 pi thirds? Well, since the denominators are already the same, you just work with the tops. Negative 19 plus 6 is a negative 13 pi over 3. Not enough. Negative 13 pi thirds plus 6 pi thirds is negative 7 pi thirds. Not enough. Keep adding. Negative 7 pi thirds plus 6 pi thirds is negative pi thirds. Not enough. Keep adding. Negative pi thirds plus 6 pi thirds equals 5 pi thirds. Well, wait a minute. We had pi thirds to begin with. So what does this work say? This work says that if I start at one angle and constantly add or subtract another angle, it is impossible for me to settle in on pi thirds, because we should notice this is too little and this is too big, right? We wanted pi thirds, but this work says if I start at negative 19 pi thirds, it is impossible to land on pi thirds by going full circles. Therefore, these two angles are not coterminal. So that's the gist of it. Finding coterminal angles, identifying if they're coterminal or not, just involves adding or subtracting full circles. Keep adding and subtracting full circles until you land where you want. Probably one of the more helpful or more important ideas in all of trigonometry is the idea of reference angles. So what is a reference angle? Well, by definition, for any angle, and this is the symbol that we typically use to denote angle theta, its reference angle and the symbol we typically use for reference angle is a little bar underneath the angle, is the positive acute angle formed by its terminal side and the x-axis. Key ideas in this definition: the reference angle is always going to be positive and acute. Acute means smaller than 90 degrees. I think this is a lot easier. Let me delete this line here. I think this is a lot easier to see with pictures than it is with words. Let's see. I think that's copy. Come on. I want to paste. I guess I should stop being lazy and just do it old school. Here's another coordinate system. They just won't be equal, and that's going to bother me, but whatever. Here's another coordinate system. And here's a coordinate system. There we go. So angles can exist in 1 in 4 quadrants. We can have an angle in the first quadrant, an angle in the second quadrant. I guess I should label it. There's theta. There's theta. We can have angles in the third quadrant. There's theta. And we can have angles in the fourth quadrant. There is theta. By definition, the reference angle is the positive acute angle formed by the terminal side, indicated as the black ray there, with the x-axis. And it doesn't matter if it's the right x-axis or the left x-axis. We just want the closest angle possible. So if your angle's in the first quadrant, notice that your reference angle is itself. If your angle's in the second quadrant, this is your reference angle. If your angle's in the third quadrant, that is your reference angle. And in the fourth quadrant, that is your reference angle. Notice I didn't put any arrowheads on the blue angles. I didn't do this or I didn't do that because I really don't care, because it's always going to be positive. So knowing what quadrant you're in is super duper helpful in figuring out what your reference angle is, because you can visualize where it is. So you're going to have one goal for this lesson, again, to find reference angles. So here's my tip to you. Know what quadrant you're in, and if you have large or negative angles, find the coterminal angle first. Right. My tips are, optional, take it or leave it, but I think it makes things a lot easier. So find the reference angle of, let's do a handful. Let's say 215. Right. Well, the first thing you need to do is visualize what quadrant 215 is in. And again, I hope it's pretty obvious if you know your degree system, right? This is 0, this is 90, this is 180, this is 270. That 215 is between 180 and 270. So I know, I'm just do a quick sketch. It doesn't have to be perfect. I think 215 somewhere is right there. So knowing that this is 215, by definition, the reference angle is the angle that the terminal side makes with the x-axis, and it's the smaller one. So I got this choice here and this choice here. You always want to take the smallest angle. So this right here is the reference angle. And the rest is just common sense math, right? So if I want this piece here, and I got this whole piece, I hope everyone agrees that we sort of overshot 180 degrees. So the reference angle, this little blue sliver here, is the difference between 180 and 215. So there you go. Easy peasy, you're done. The reference angle is the difference between 215 and 180. So 45 degrees, 35 degrees is his reference angle. What if I ask you something ridiculous? What is the reference angle of 1780? Well, again, that's a really big angle. So my suggestion to you is don't work with 1780, work with this coterminal angle. Now I'm not going to I'm not going to show all the subtraction. I hope you guys understand how to find coterminal angles. Just subtract a full circle. In this case, just keep subtracting 360. So I know just by doing this ahead of time that 1780 is coterminal with 340 degrees. Now I can find the reference angle. Where's 340 degrees? Well, I know he's in the fourth quadrant. That means visually, here is his reference angle. Well, I know that this x-axis is 360 degrees, so the reference angle must be the difference between 360 and 340. So the reference angle here is 360 minus 340, which is 20 degrees. Again, we need to be comfortable with degrees and radians. So if I ask you to find the coterminal angle, the reference angle at 7 pi thirds, right? We should recognize that 7 pi thirds is beyond a full circle. How do you do that, or how do I know? Remember that a full circle is 2 pi radians. So you just look at the numbers here. Notice how these numbers are bigger than the number 2. 7 thirds is bigger than 2. So I know I can find a coterminal angle. So the coterminal angle of 7 pi thirds is actually just pi thirds. So if I sort of imagine where pi thirds is in, remember in the radian system, this is 0, pi halves, pi, 3 pi halves. I know that pi thirds is somewhere in the first quadrant, so this is pi thirds. Well, the reference angle is always to the x-axis, so do you see how that's the same angle? So this one is pretty easy. We don't have to do any math. By default, since it's in the first quadrant, the reference angle is pi thirds. Let's do something a little bit more interesting. Let's say I want to find the reference angle 5 pi fourths. Again, what quadrant is he in? In the radian system, 0, pi halves, pi, 3 pi halves. You just look at the numbers without the pi. So 5 fourths is a little bit over 1. Right, so this right here is 0.5 pi, this is 1 pi, this is 1.5 pi. So 5 fourths is a little bit more than 1, so I know that this angle is somewhere in the third quadrant. Right. So if this right here is 5 pi fourths, visually that is the reference angle that I'm looking. So I hope you guys can see that this reference angle is simply the difference between 1 pi and 5 pi fourths. So there we go. We're done. The reference angle is 5 pi fourths minus 1 full pi. Of course, to add and subtract fractions, you got to get the same denominator. So 1 is the same thing as 4 over 4, which of course is pi fourths. So those are the lesson objectives. We have to be confident with finding coterminal angles, converting between degrees and radians, and finding reference angles. That is 5.1.